Let's discuss transformer secondary protection and how it relates to the National Electrical Code, specifically Section 240.4F and Table 450.3b, particularly concerning a 480 to 208Y/120 transformer. Also, let's examine how to determine the voltage ratio of a transformer. According to Section 240.4F of the National Electrical Code, secondary protection is indeed required from Table 450.3b for a 480 to 208Y/120 transformer. Section 240.4F, titled Transformer Secondary Protection, states the following: F. Transformer Secondary Protection. Where the secondary voltage exceeds 601 volts, the secondary winding shall be protected by a continuous secondary overcurrent protective device. Where the impedance of the transformer limits the current to less than the value specified for the overcurrent protective device for the size of the conductor used, the overcurrent protection shall be permitted to be omitted. Based on this, because the secondary voltage of the transformer in question, which is 208Y/120 volts, does not exceed 601 volts, this section of the code does not require secondary protection. However, Table 450.3b dictates the overcurrent protection for transformers rated 600 volts or less. Therefore, to correctly interpret the requirement for secondary protection, you must consult Table 450.3b. Table 450.3b provides guidance on the maximum overcurrent protection allowed for transformers with a primary voltage of 600 volts or less. This table typically differentiates between primary and secondary protection requirements based on the transformer's impedance. For transformers with an impedance not more than 6%, the overcurrent protection on the primary side shall be set at no more than 125% of the transformer's rated primary current. On the secondary side, the overcurrent protection should be set at no more than 125% of the transformer's rated secondary current. If the transformer impedance is more than 6%, the primary overcurrent protection can be set at up to 250% of the rated primary current, while the secondary protection remains at a maximum of 125% of the rated secondary current. Now, let's address how to determine the voltage ratio. The voltage ratio of a transformer is the ratio of the primary voltage to the secondary voltage. For a 480 to 208Y/120 transformer, the voltage ratio can be calculated by dividing the primary voltage by the secondary voltage. To calculate, one divides 480 by 120, which equals 4. This means that the transformer steps down the primary voltage by a factor of 4 to produce the secondary voltage. Understanding the voltage ratio is crucial for several reasons. Firstly, it helps in selecting the appropriate transformer for a specific application. If you need to step down 480 volts to 120 volts, a transformer with a 41 voltage ratio is suitable. Secondly, the voltage ratio is used to calculate the current ratio, which is the inverse of the voltage ratio, assuming an ideal transformer. This information is useful when sizing conductors and overcurrent protection. Thirdly, the voltage ratio is essential for understanding the transformer's impedance and its impact on fault current levels. The impedance of a transformer limits the amount of current that can flow during a short circuit. A higher impedance results in lower fault current levels, which can affect the selection of overcurrent protective devices. Now, let's elaborate further on transformer protection. Transformer protection is essential to prevent damage to the transformer and to minimize the risk of fire or electric shock. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect the transformer from overloads and short circuits. Overload protection is designed to protect the transformer from excessive current flow caused by loads exceeding the transformer's rating. Short circuit protection is intended to protect the transformer from high fault currents caused by a short circuit in the transformer or the connected load. The selection of appropriate overcurrent protection devices is based on the transformer's voltage, current, and impedance ratings, as well as the applicable codes and standards. In addition to overcurrent protection, transformers may also be equipped with other protective devices, such as temperature sensors, pressure relief valves, and differential relays. Temperature sensors monitor the transformer's winding temperature and can trip a circuit breaker if the temperature exceeds a safe limit. Pressure relief valves are designed to relieve excessive pressure inside the transformer tank, which can occur during a fault or overload. Differential relays compare the current entering and leaving the transformer and can detect internal faults that may not be detected by overcurrent protection devices. When selecting a transformer, it is essential to consider the application-specific requirements, including the voltage, current frequency, and load characteristics. It is also important to consult with a qualified electrical engineer or contractor to ensure that the transformer is properly sized and protected. Furthermore, regular inspection and maintenance of transformers are crucial to ensure their safe and reliable operation. This includes checking the oil level, inspecting the bushings and connections, and testing the protective devices. Understanding these principles ensures electrical systems operate safely and efficiently. Proper installation, protection, and maintenance contribute significantly to the longevity and reliability of transformer operation in electrical distribution systems.